Here looks funny. I don't know what's going on there. Ugh. The mirror makes it worse. Anybody have any questions before we get started? It's about time for class to start. Actually, it just turned time for class to start. So, anyone? We only got 5 of us in here, but I'm going to go ahead and get started because we got a lot to do. We had finished the section on abuse of art. Of course, we didn't have class on Tuesday this week due to the election. So now I want to go, now that we've used the law of abuse of art to figure out some of the more complicated charge distributions, which really were just a loop. We also did a quarter circle and then another quarter circle back that made sort of a circle using the law of abuse of art, and gave you a very general conclusion to make on that when you have such circuits where part of the wire is part of an arc and you wish to know the magnetic field at the center of that arc, and then other parts of it are other arcs with the same center, are radial lines that point away from or towards, depending on which way you're going with the current, away from or towards the center of the arcs for those guys. So there was a very specific conclusion we were able to make about that. And we did an infinitely long line of charge. Now we're going to show you another way, so not unlike what we did with electricity and electric fields. Specifically, we introduced Coulomb's law, which was kind of complicated, not as complicated as abuse of art, but still pretty complicated. And we were able to find the magnetic field, or excuse me, the electric field due to a charge distribution along an infinitely long line and along an infinitely large plate and various other things like that. But then we came back and showed you another way that was easier using Gauss's law. We're going to do the same thing now using what's called Ampere's law. And here I go yawning again. I literally have not yawned at all today until just now. So I don't know. Anybody have any questions before we get started on this? All right, I'm going to go ahead and share screen then. So first off, I want to start with the idea of there existing something called the magnetic flux. And by that, I mean the flux of the magnetic field, which is defined the same way as the flux of the electric field, except in the place of E, we're going to put B as in boy instead of E as in electric. So B is in not magnetic field, because it starts with an M. But anyways, so first off, what we're going to do is we're going to say there exists something called the magnetic field flux, or magnetic flux, which is the integral of B dot dA. Okay, so notice it looks just like the electric flux, which we did with Gauss's law before. So all the same stuff you learned about that is applicable here. The only difference is the units that we're using for B are the Tesla, and therefore the magnetic flux comes out in units of Tesla times square meters, which is defined to be the Weber. Okay. So you can remember that in terms of a gas grill, for instance, but there's the term that we use for it. And you'll see how that contributes for once we cover, for instance, Faraday's law. You'll see how the Weber is related to voltage and stuff like that, for instance. So once we have that basic definition of what the electric flux is, then I can tell you what Gauss's law is, or excuse me, what Ampere's law is. In order to do so, though, I don't know why I did that. Scratch that. I don't even know why I told you about magnetic flux. I just remembered I've been doing Faraday's law in my 202 class instead of the 242. So I just introduced that. So we can get rid of that completely. I apologize. Completely forgot where I was here. We are going to use it, don't worry, but it's not ready yet. What we're using here is something different than, good Lord, I can't believe I did that. It's something different than the flux. In this case, we're going to do something odd. It's going to be a line integral. And the line integral can be related to a surface integral in a different dimension sort of thing. So it's basically in converting the differential equation that's known as Ampere's law to the integral equation that's known as Ampere's law, we end up getting this line integral. And what Ampere's law is the following. So let me write this down. So this is going to be called Ampere's law. And basically what Ampere's law says is the closed integral. So see, it's got that little circle on the integral symbol, just like Gauss's law did. And again, it doesn't do anything different mathematically. It's no special kind of integral, but it reminds us that, hey, this equation only applies when you deal with, in the case of Gauss's law, it only applied with a closed surface, but in the case of Ampere's law, it only applies to a closed loop. So what we have is the closed integral of B dotted with DL, a differential line element, is equal to mu 0 times I enclosed. So if you remember correctly, Gauss's law was the closed integral of E dot dA, which is part of why I went into that diatribe about the magnetic flux. But that turned out to be Q enclosed over epsilon naught. So that was what we knew of as Gauss's law. And you can see how that's somewhat similar. Specifically, the right-hand side has an enclosed quantity. And Gauss's law, it happens to be the charge enclosed, and it means enclosed inside of that closed surface that the integral is referring to. In this case, Ampere's law, it's a closed loop. So you basically have a loop that you're picturing. It doesn't have to be a physical loop. It could just be something you're imagining. And all the current in that closed loop is what goes on the right-hand side multiplied by mu 0. And there's a very specific sign with it. For instance, if we imagine a loop like this, okay, so I'm drawing part of it looks kind of dashed, and that's supposed to be back behind my screen, and the solid part's supposed to be out in front of the screen. And for instance, if we go if we do this line integral in this direction, as shown here, then what I want to do is take my right hand and curl my fingers in the direction that I'm integrating. And then my right thumb points in the direction of positive current. So according to the right hand rule, then this direction is a positive current direction. But this direction would mean a negative I, which means I is less than 0. So that's the sort of corresponding rule. Just like when we did Gauss's law, we had a rule where the differential area element A would point out from, as if it came from the center of the enclosed surface towards the outside, and that would make a positive dA. In this case, we're defining a positive current with something like that. So they're somewhat related, but obviously not completely, because really all that mattered as to whether you got a positive flux or a negative flux was whether the charge enclosed was positive or negative. In this case, you actually get something quite different. So if you look at this, we're going to do sort of the same thing that we did again with Ampere's law. Remember, Ampere's law, we tried to solve for we solved for the integrand. And specifically, we really solved for the magnitude. So we I'm going to write this down. So what we did is we had to have some understanding of how electric fields behaved, or how electric fields oriented themselves around specific symmetrical charge distributions, so that we could get an idea of basically what directions they'd be in. And then what we tried to do is come up with a Gaussian surface on which either the electric field was exactly perpendicular to the surface, which we defined to be parallel to a dA vector, or it was exactly perpendicular to the dA vector, and therefore the dot product would give us 0. So by doing that, that allowed us to extract the integrand. We're going to try to do the same thing here. Is we want to solve for this. So obviously, you have to sort of understand how the magnetic field forms for a given symmetry. The symmetry that we use for Gauss's law, for instance, was that the charge distribution had to be cylindrical, infinitely long and cylindrical, or it had to be spherical, or it had to be infinitely large and planar. Oops. In this case, there's going to be a symmetry issue as well. And in this case, we need, again, we need a cylindrical current. In other words, a current that basically goes infinitely long in a straight line. Or we could use, for instance, multiple currents going infinitely long in a straight line, so that the magnetic field would have a constant value on a cylindrical surface, something like that. We could also use, for instance, a solenoid, or we could also use a toroid, and we're going to do all of that. By doing that, that allows us to get a magnetic field that's either always parallel to the dl vector, which points in the direction of the current, ideally, or excuse me, in the direction of the magnetic field, ideally, or it's going to be B is perpendicular to the dl, which again is a little line segment, a little tangent vector on the curve. So you can look at, for instance, here, you could say this is a DL. Notice it's tangent to the curve at the point, and it actually points in the same direction we're integrating around. What we ideally want is to make sure that the B is parallel to it everywhere, or completely perpendicular to it, or 0, so that everything cancels out except for the magnitude on the places where B is parallel to DL. So that's a lot of words. It's and there are a lot of quote unquote correct words. So it's not like I told you something that was wrong. I just told you something that, despite hearing it, is still not very easy to make sense of. So what we do is we go ahead and work an example. And the easiest example is an infinitely long wire, just like the easiest example of using Coulomb's law and of using well, the easiest example of using Coulomb's law was a infinite charge distribution along an infinitely long line. And now we can do the same thing with this, but it's a current that's along an infinitely long line. So what I'm going to do is I'm going to imagine a current coordinate system. Again, you don't have to have the coordinate system to solve the problem, or to be given the problem. All you have to do is be given a current carrying wire, and then as long as it's got the appropriate symmetries, you can then make up your own coordinate system to help you conduct the left side of that integral and compute the right side of that equation. And in doing so, you can determine the magnitude of the magnetic field. So let me start by drawing just a wire. So we're going to imagine a long wire like so. And let's say it's fairly thin, but the important point is that the current is going to be going up like this. And I'm going to say that this will in fact go on for infinity. So the wire goes on for infinity that way and goes on for infinity that way as well. Now I'll draw my coordinate system, and what I'm going to do is go right down the middle here like this. And that's going to be, in principle, the z-axis, which for some reason the drawing it myself application didn't work so well, but hopefully it will now. Oops. Of course not. So that looks pretty good. I'm going to say that that is my z-axis. So I'll put Z right there. And there's a reason I'm doing Z. It's so I can make use of a coordinate system that exists. Even though you don't necessarily have to know these special coordinate systems, it does help a lot when you do. I'm going to now take and say the y-axis points to the right, like this. And I'm going to say the x-axis, whoa, no, the x-axis points out of the page. So this is our x-axis, this is our y-axis, and that's our z-axis. And you should be able to confirm that it is, in fact, a right-handed coordinate system. That's the important thing. Again, like I told you before, you can get in a lot of heap of mess if you make a coordinate system that actually accidentally turns out to be a left-handed coordinate system. So just always make sure that I hat cross j hat gives you k hat. And if you don't do that, it could, like I said, give you some problems. So what I'm going to do is imagine, again, this is a current. It's actually going in the positive z direction, and it's symmetric, or it's centered on the z-axis. So the actual center of the wire runs right along the z-axis with the current going in the positive z direction. And just because we're used to finding the magnetic field a distance r away, I'm going to use that to label the distance on the y-axis. I could do the distance on the x-axis, doesn't really matter. I could do the distance r somewhere halfway between the x-axis and the y-axis, or between the negative x-axis and the positive y-axis, all sorts of stuff I could do. But the main thing is I'm going to do it on the y-axis. So what I'm going to do is I'm going to come over here on the y-axis, and I'm going to say that this distance right here is a distance r away as measured perpendicularly to the current. So that is basically the minimal distance. And in order for me to apply Ampere's law, I want to find a loop. So I want to find like a infinitesimally narrow closed loop, and I want that closed loop to be oriented such that the magnetic field, due to this current carrying wire, is everywhere parallel to the tangent vectors of that little current, or excuse me, of that little circuit. So we're going to imagine a circuit or a loop of wire or a loop in space. It doesn't really have to be a wire at all. It doesn't have to be any real thing, but we're just going to imagine a path that is closed, and any closed path would do, but we can't do Ampere's law unless the closed path works out certain ways. And the way that we want it to work out is that the B would be parallel to the tangent vector DL at everywhere, or it better be 0, or it better be perpendicular to DL. So if it's not a constant on that circuit, that circle that we're doing, then it better be 0 on that circuit, or it better be perpendicular to DL on that circuit. So hopefully y'all understand sort of what I'm saying, but I think you understand by the right hand rule, if I took my thumb and laid it along that current carrying wire, thumb of my right hand, and then wrap my fingers around the wire, you would see that looking down towards the XY plane from above the positive Z axis, way up in the positive Z area, when I look down, that would actually cause me to see the magnetic field lines being in a counterclockwise direction. Okay, that's the same direction that I want to make my loop and my integral, and it's also the same path that I'm going to follow, because if I choose a constant r away from the center, then the distance away from the wire will be the same everywhere, and that should be the only thing really that the magnitude of the magnetic field would depend on. So what I'm going to do is start off and say, here's the question: what is the magnetic field at position X, Y, Z is equal to 0, R, 0. Okay. So to work this problem, I'm going to say solution and we're going to use the closed integral of b dot dl is equal to mu 0 I enclosed. Oops. And we're going to use the hypothesis that b, the vector, is equal to, I suspect it's only going to depend on the distance r. Okay. So I'm going to say it's b of r, meaning its magnitude only depends on the variable r. And it's going to point in what you might recognize as the theta hat direction. Because remember, if you talk about theta, like in polar coordinates, the theta is measured counterclockwise from the positive x-axis. So for instance, over here, let's say with this arrow, right here, theta would point that, or theta would increase in that direction. And then here it would increase in that direction. And then here it would increase going into the page. And then back here it would increase going that way. And then back here it would increase going out of the page, so on and so forth. So that makes all of that the what we call the theta hat direction. So I'm going to call it that, even though in reality we can pretty much derive it as some kind of vector. So I'm just going to call it theta hat, going on the assumption that we have some familiarity with what it is. Remember, a hat symbol always means that it's a unit vector. So that's my hypothesis about the magnetic field strength. And because of that hypothesis, I'm going to say the loop that we're integrating over, which is a loop or a path or a line, and I don't mean line in the linear sense, is basically R, whoa, crap, is basically R equals a constant. And this time I mean R, the polar coordinate. And in fact, we specifically say the constant is equal to R. And actually, because of that, let me change this to a capital R just to make it a little easier and less confusing. So I'm going to say it's big R like that. So that's the actual path that we're going to integrate around. And it actually has a directionality. So I'll say that basically the path, basically we could say that the path is going to be a closed circular loop, and it's going to look like an ellipse in here, but let's see if I can draw it. I'm going to say it goes, oops, not that either. I'm going to say it goes something like this. Like that. Okay. And what that means is I am going to integrate around in this direction, because that happens to be the same direction as the magnetic field. And by the way, notice that if I curl my fingers of my right hand in the direction of that integral, my right thumb sticks up, which is actually parallel to the current, and therefore the current I can record as a positive quantity. So that's my actual, what we call Amperian loop. Okay, so that's the Amperian loop. That's what we're going to integrate around. So now all I have to do is take the left-hand side And this is just like Gauss's law, where you have to work the left-hand side, then you have to work the right-hand side, then you have to set them equal to each other, and then you have to solve for the integrand. That's what we're shooting for in this particular use of Ampere's law and that particular use of Gauss's law. There's other ways, you know, it's actually called Gauss's law, and in this case, it's actually called Ampere's law. So it's always valid. But to do this weird thing where we're trying to extract the integrand, it has to have these very specific symmetries and all that stuff to be true for us to do that. So that's what I'm going to do. I'm going to say the left-hand side is in fact equal to the closed integral of b dot dl. I am going to say that dl is this. So let's imagine for a second that I come out from an angle theta. So this is the angle theta right here. And then I allow that to increase a little bit by an amount d theta. And then I'm going to take a tangent vector right there that's about the length of the distance between those two lines that I just drew. In other words, that the crust of that pizza slice or that pie slice that you're seeing there. Actually, let me zoom in and make it a little more exacting regarding the length of it. Okay, so you can sort of take that chord length and now you can say, okay, well, dl is a vector quantity. So I'll put an L on top of it. And we will say that the arc length around there is actually r times d theta. And that just comes from the equation S is equal to r times theta that we know of from trigonometry. But it is a vector, so it actually has to point in a very specific direction, and that direction is the, oops, used the wrong color. That specific direction is the theta hat direction. Okay, again, you don't necessarily have to know that the theta hat even exists or anything. You're just trying to think of, hey, if I go to any point in the XY plane, and I draw a line from the origin of the coordinate system to that point, then that line will be radial. If you draw it from the point to the origin, it's radially inward. If you draw it from the origin to the point, it's radially outward. And then if you go ahead of that by 90 degrees, or actually sort of, you can sort of say ahead of it by, yeah, just basically 90 degrees, then that's the direction in which theta increases, and that's our theta hat direction. And you can see that clearly the theta hat direction is exactly what the L has. So we've got our hypothesis about B, we've got our dl, so I can now say that the closed integral of b dot dl is going to be equal to the integral, and the b, remember, is b of r. In this case, it's actually b of capital R since I've changed it now. So let's put that there because it's specifically on this line, on that circuit, which has a radius big R. So it's b of r theta hat, and that's dotted with r d theta theta hat. And we've been mentioning this before, but the dot product is what we call a linear operator. So I can pull all the non-vector stuff out in front, and I'm going to say b of r times d theta times theta dot theta hat. So theta hat dot theta hat. That's basically the linearity allows us to pull all the non-vector stuff out in front. And then, of course, theta hat dot theta hat. Does anybody recall what theta hat dot theta hat would be? Remember, the dot product has a magnitude given by the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So in this case, that means it's 1 times cosine of 0, which gives us 1. Okay. Now, the fact that this b of r has a very specific r value, r, and the r itself is a very specific r value, that means they're constants, and we can actually pull them out in front of the integral. So that's what I'm going to do now. I'm going to say B of R times R times the integral of d theta, and theta is going to go from 0 to 2 pi, which we get is 2 pi r times B of R. So does everybody follow what the left-hand side is and how we got all that? Anybody have any questions on that? All right. So now we do the right-hand side. And the right-hand side is mu 0 I enclosed. So all we really have to do is check how much current is actually going through that little space between the lines. So for instance, you have a circular hole, if you will, that's defined by that blue oval that I've drawn there. In reality, it's actually a circle. It's just we're looking at it in 3 dimensions or in 2 dimensions, and it's a 3-dimensional representation or 2-dimensional representation of a 3-dimensional shape. So if we actually looked at it, it'd be a circle, and basically any current going through that space that's spanned by the circle. In other words, the circle sort of limits an area. All the areas that have as their edges would be acceptable, and any current penetrating that area is going to count in the I enclosed. So it could be, for instance, the area that's just the flat plane from the right side of the circle to the left side, from the front of the circle to the back side. Or it could be a sack, like a garbage bag, whose top has been opened and is exactly the shape of that circle. And then the bag is whatever surface comes below it. So anything piercing that bag, which of course is spanned by the, or spans the actual circuit, all of those would be included as well. That's going to come into play later. So right now I see exactly one current, and that current is I, and that current in fact is consistent with the right-hand rule. So we can call it a positive current, and I'm just going to say this side is mu 0 times positive I. Any questions on that?
So if you had multiple currents there, like if they were going in opposite directions, would you just like add and subtract them?
Yes, if you had 2 of them, one would be positive because the one that's obeying the right-hand rule, and then the other one going down, which you'll see in another example, would be counted as a negative. Yep.
And then if they were at like angles off in like different directions, I'm assuming you would like use trigonometry to find their components, or
No, all that matters is not really any vector components of it, but whether it's consistent with that right-hand rule. And it gets well, it'll help you just to see more examples, because you see there's pretty much like 3 problems that we can solve, maybe 4 problems that you can solve with Ampere's law. And once I've shown you those 4, you've seen every example. So that'll
okay.
make it a little easier for you. All right, so now I can set the left-hand side equal to the right-hand side. That's going to give me 2 pi r times B of R is equal to mu 0 times I. And now I can go back and recall what my hypothesis was, and I've reached the conclusion that B is equal to mu 0 I over 2 pi r, all of that being in the theta hat direction. So that's it. And that's the same expression that we found when we did the law of Biot-Savart. We found it was mu 0 I over 2 pi r, and that pointed in that very specific direction. So you see that this did actually give you what you expected to get, hopefully. Does that make sense to everyone? All right, let me show you the 2 more simple, 2 of the other simple ones, and then we'll try to do a fairly hard one. So let's go to the simple one. And the simple one I'm first going to do is a solenoid. So what we're going to do is we're going to imagine that there is a wire coming down like this. And let's say current is going this way. And then that wire is going to make a loop like this and then smoothly come back and make a loop like this, and then smoothly come back, and then smoothly come back, and then smoothly come back. So it's going to make what you recognize as the typical electromagnet, but without the piece of metal in the middle. So each of these is a loop of wire, and they're going to be packed as close as possible just for making it nice and uniform. Like that. And then finally, this last bit of wire will come up and go straight like this, and the current will go that way. That's called a solenoid. So what is the magnetic field inside the solenoid of length L with N turns? Okay, so what we're saying here is this length from here all the way to here is L, and the number of turns is equal to N. Okay. In order for us to do this, I need to look at a cross section. So I'm going to imagine an itty bitty part of it, say, and do that. So let me draw it again. We see that the wire is going from back behind the screen, and then it comes out towards the front of the screen, and in fact comes out of the screen and goes up. So what you should realize is that some small part of it is ended by a current coming out of the screen, and then up above it is a matching current, but this time it's where that one's going into the screen, and then this one's out of the screen, in the screen, out of the screen, in the screen, like that, like that, like that. And we just keep on doing this basically for some fraction of the total length of the solenoid. And I'm going to call that length lowercase l. Okay. Oops, wrong one. Okay. So let's say this distance right here is going to be lowercase l. We know that the turn density, let's say this, the turn density, this is a phrase I'm making up right now, of the solenoid is N turns per length L, or N over L equals lowercase n. So we can define N divided by L as lowercase n. So everybody follow what I'm saying about that? Thanks, Taylor. All right. So now what we can see is if we look at those little wires along the bottom, notice their current's coming out. So we take our right hand and we pull our thumb towards us. And now we look at our fingers, and what we see is, and let's do it over here, just to make it a little clearer while we're seeing stuff. And God, that was an awful, whoa, no, that was an awful circle. I hit the wrong arrow. Let's do this. Let's do this. So what I want to do is imagine this little circle of wire, And again, taking the idea that our right hand has our thumb pointing out towards us, that's what that little dot in the middle means, right? That means right here, the magnetic field will point this way. Right here, the magnetic field will point this way. Right here, the magnetic field will point that way. And then right here, the magnetic field will point that way. And even on the diagonals, it's going to be diagonal like that. Okay, so hopefully everybody follows that. Now, if I put another one right next to it, this will be important as well. Okay, now I can take and put another dot in the middle. Another dot in the middle. So you see what's going to happen with this wire next to it is it's going to have a magnetic field pointing this way here, pointing this way here, pointing this way here, pointing this way here. But the main thing is you see that right here between them, notice the magnetic fields cancel each other out. And notice also that this creates, let's use green for my magnetic field. So I'm going to change my pen color. This creates basically a magnetic field that points this way. And in fact, it can make a very strong magnetic field in the center. Okay. So with that in mind, what I'm going to do is create a coordinate system. And that coordinate system is going to be basically a y-axis this way and a x-axis this way. And now I'm going to do solution. I'm going to say hypothesis. The hypothesis is that B is going to be equal to B of Y, meaning I only think it's going to depend on Y, times I hat, or inside the solenoid. And I'm going to say it's approximately 0 outside. Okay. And of course, you can see it's approximately 0 between the individual wires. That's why I showed you that little blue circled spot. Okay.
Would it not do the same thing on the outside? Like just make a magnetic field going in the opposite direction?
It will, but what happens is all of the sort of energy goes into creating this magnetic field, but down the center of the solenoid, and the magnetic field lines come out of each end. Of course, it comes out the left end, like that's the north end of a bar magnet, and then loops back around and comes back in the right end, comes back into the right edge of the solenoid. So the vast majority of the magnetic field energy is really inside the solenoid, and the lines are so far apart outside the solenoid that it's really weak compared to the extremely strong solenoid or magnetic field inside the solenoid. In fact, if you actually get an MRI, the MRI itself is a solenoid. That's why you've got that narrow little tube for you to slide down. They basically have a huge bunch of wires going around this, and you're laying inside of there, and it makes an extremely strong magnetic field. In fact, I saw on Twitter, or X as Elon Musk calls it, just this weekend, a guy named Massimo, Massimo, tweeted a video where some people had just got a brand new MRI device, and they held up their car keys like by the end of the MRI device, and it just sucked them in there. And then another guy picked up a folding chair and it sucked it in there, and they couldn't get it out. But anyways, you can just see that the magnetic field exists outside, but compared to how strong it is inside, it's almost nothing. Does that make sense?
Yes.
Okay, so that's what we're going to do. Now, what I'm going to do is I'm going to make a path for this loop in Ampere's law. So the path for me, I'm going to actually go from right here straight along this way, and then I'm going to come straight down. And any distance out here would be fine. I'm just trying to get it out of the way of my words. And I'm going to integrate it around in this direction. Okay. Does that make sense to everyone? I will call this A, B, C, and D. So now we can work with the left-hand side. The left-hand side says the closed integral of B dot dl is equal to, it's going to be the integral from A to B plus the integral from B to C plus the integral from C to D plus the integral from D back to A. Okay. So now I think you can, I'm going to do the DLs on the fly. I think it'll make perfect sense when I actually do it. So I'm going to say B from A to B is going to be B of Y I hat. And then the DL is going to be DX I hat. And this is from basically A to B. So I'm going to say I'll just say from A to B. Like that. Plus the integral of B of Y I hat dotted with, in this case, I'm going to say negative dy j hat, and that's going to be from B to the edge. And what I mean by the edge is, remember, we're basically going to get to the edge of the actual wires, and the magnetic field is going to start disappearing right there. So then I'm going to say plus the integral from the edge to C. And in that case, we're going to get 0 dot negative dy j hat. Okay, so in other words, my integral from B to C actually became two different parts. There's the part where the magnetic field exists, which is really between these two lines right here. Okay, that's where the magnetic field wasn't 0, and then the rest of the way the magnetic field was 0. So I took this time to show this this two integrals specifically so you'd understand what's going on. You don't have to show me all that stuff. I just wanted you to understand how it's going on. So now I'm going to continue with plus the integral, and in this case it's from C to D of 0 dot, in this case it's negative dx I hat, plus the integral from D to the edge, and this time it's going to be 0 dot dy j hat, plus the integral from the edge to A of B of Y I hat dotted with dy j hat. So again, this is just me showing you exactly what's going on. It's way more than you need to show me, because at the end of the day, just like when we did Gauss's law, the left-hand side is supposed to become E times a surface area. In this case, it's Ampere's law, and the left-hand side is supposed to become B times a length, or B times a length plus B times another length plus B times another length, and that sort of thing, sort of like Ampere's or like Gauss's law used to allow us to do as well. So I'm going to pull this down here. And now what we'll see is for the integral from A to B, I'm going to get the integral of B of y times dx times I hat dot I hat. And of course, I hat dot I hat is just 1. And then you can see the integral from the B to the edge, since it's I hat cross J hat, you're going to get 0. I'll show you that by saying it's B of y times negative dy times I hat dot J hat, which is 0, plus 0, and this part was from the B to the edge, and this part is from the edge to the C. That's what the 0 was, but we don't have to show that. Plus, continuing that same line, you can see the integral from C to D is equal to 0. And just for the record, I'm going to say, using this blue line, this part right here is that one, and this part right here is this one. And then, of course, this would be this integral plus, plus, now I get another 0 from this integral, and then another 0 from the other integral. Okay. Now you can see that this B of y, since we're taking it on a constant y, the B of y comes out in front, and ultimately the line integral just becomes B of y times the line integral, which is just the length of the line. So this first integral is going to become B of y times L. So that's what the left-hand side is. So again, notice we're just getting the typical scenario, which is a magnetic field magnitude times a length. So that's what the left-hand side became. Now the right-hand side, which is the one that's potentially more difficult, is mu 0 I enclosed, which is equal to mu 0. Now notice with my finger sticking out the direction of the current, my fingers curl, my thumb sticking out, my fingers curl in this counterclockwise way, which is the same direction that I integrated around that loop A, B, C, D, A. So all of these currents are positive, and in fact, the number of those currents is the number of wires going through there, which if you multiply little n times L, you'll get the number through there because the density is little n. So I'm going to say this is now little n times I. So that's the right-hand side. Any questions on that? So now I'm going to say left-hand side equals right-hand side. And that gives me B of y times L is equal to mu 0 n times I. Oops, n times I times L. Sorry about that. Remember, I have to actually multiply n times L to get the number of current carrying wires. So I don't know why I left off that L, but that's why that has to be there. So now you can see that the L's cancel out, and ultimately the magnetic field that we found was, using our hypothesis, B is equal to mu 0 n times I inside and 0 outside. And at all points, of course, in the I hat direction. So I'll put that there and this there.
So for the whole thing, would it be big N instead of little n?
Well, what matters is really the density, because we actually still have to multiply it times whatever length we have. So the answer is actually, or let me say this, another way of writing it would be Bn is equal to mu 0 big N I over L. That's another way of writing, and it's perfectly acceptable as well. So yeah, it's got to be the N over L as opposed to the big N.
Got it.
Okay. So any questions on that one? Okay, so that's one of quote unquote the simple ones. The current carrying wire is a fairly simple one. The solenoid is a fairly simple one. Now what we're going to do is imagine that solenoid being really, 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 really long, right? Really long. And not only that, it's a little flexible. So I'm going to turn it around and bend it and make it into a donut. At that point, it becomes what we call a torus or a toroid. And that's what we're going to do now. So we'll say, what is the magnetic field in a torus? Actually, let's call it a toroid, because I think technically that's correct. Toroid of, damn it, I keep writing R there, of radius, and I'll explain this with a drawing in a second, R, total turns in, and carrying a current I. Okay. So that's the big question. So now let me draw what I mean by a torus. I am going to imagine a circle. Okay. And now I'm going to imagine another circle inside of that that is obviously smaller, like that. And in fact, what this represents is, let's look at it this way. Let's say there's a wire coming in. Dang it. Let's undo that. I'm going to say there's a wire coming in like this. And then that wire goes around and around and around and around and around like that. So if you think of it this way, then we'd say the current in this case is coming down here. And that means if we took just a little chunk of it, we would look like this. We would have, now I'm going to use the actual simplified drawings. And then up here, we're going to have some more circles. So I'm just trying to zoom into a little section here. And what you'd see is the way this is working is we're actually going to have a bunch of currents going into the page on the inside and a bunch of currents coming out of the page on the outside. At least that's the way I've drawn it in this particular diagram. And then ultimately it'll come back around here and you'll see this guy like that with the current going that way. So I think you can tell from this that using the right hand rule, if I grab those wires at the top, then my right thumb should be sticking out at me and my fingers would curl around them and make the ultimate magnetic field through it go this direction. Okay. Does everybody get that? You can also do the bottom wires, only there the current's going in, so you have to point your finger away, and you'd see that then inside they're going to the right, so that makes the magnetic field go around that way. So what I'm picturing in the big diagram is magnetic field lines going in a clockwise direction, or excuse me, counterclockwise direction around here. And actually, I really should have done this with my drawing thing on. Let's see if it makes it better this way. It might not. It's probably going to make some weird arc. Yep, I knew it would do that, jerk. Okay, but the main thing is I think you can see that the magnetic field is going around this in a counterclockwise circle, something like that. Does that make sense to everyone? Okay, now I'm going to erase all that because that's the ugliest drawing I've ever seen in my life. So I'm going to erase all that little green marks, but I think you understand what's going on. So what I'm going to do now is I am going to choose a path. And the path I'm going to choose is this one. Okay, so that's my actual path. Ooh, not that one. Okay, I'll just have to leave it then. All right, that's my actual path. And specifically, specifically, I'm going to go around it in this direction. Okay, now I'm going to put a coordinate system on here just so I can make use of some of the symbols that we use. In this case, I'm going to draw a x-axis that way and a y-axis this way. Okay. And what I mean by that radius r is really that the distance from here to about here is r, and then the distance from that end to the inside coil or the outside coil is infinitesimal. It's so small we don't care about it. In other words, it's got to be at least a factor of 10 smaller. So for instance, if you had a big toroid whose radius was let's say 10 centimeters, then I would want the distance from the inside wires to the outside wires to be no more than a centimeter, but preferably a little less. So that's what I mean when I said the big R. So anybody have any questions on what's going on here? This red wire, this red circuit right here is the Amperian loop. Okay. So now I can do solution. First off, I'm going to say that B is equal to, this is my hypothesis, so I should probably write that too. So let's say hypothesis. B is equal to, let's say, B of R. And actually, I should say B of big R because that's the radius I'm dealing with. So B of big R times theta hat. That's why I chose to draw the X and Y axes this way, because you can see that everywhere the arrows on that Amperian loop are pointing in the theta hat direction. And I'll say this is inside. Okay, I don't care about the outside, so I could just say like this, 0 outside. So that's my hypothesis. And the equation I'm going to use is B is equal, or B dot dl, the closed integral, is equal to mu 0 I enclosed. Okay. And notice these wires. Let's see if this is really the way I want to go. Oops. No, that is not the way I want to go. Crap, boob, crap. So let me do this. All these arrows that I drew are the wrong direction, which means it's a bit of a problem.
I mean, couldn't we just swap it, like swap like like a negative sign at the end for a positive
Yeah,
sign?
the only thing is I really, well, yeah, if I went and drew this back where I put the circles inside going, let's say, coming out of the board, yeah, that would be better. Let's do it that way. I'll leave the circles and the directions in here as they are. So the red lines, for instance, are still going to go this direction. And then, of course, I'll complete this little circle right here since I accidentally did that. What I'm going to do to change all this is,
Swap the arrows on the eyes and
yeah,
then
that's what, yeah,
switch the axis
exactly.
for dot.
So that, all those are going to become dots.
So we're basically just looking at the torus from the other side, or the
Yeah,
toroid.
essentially, yeah, exactly. And that, of course, makes the magnetic field go the opposite way as well. These aren't too bad. I can just draw an X on it like that. Okay. And now I'm going to fix that by seeing all of these guys are going this way. And that's my magnetic field. Okay. So everybody follow that now? Sorry about that redirection. I completely forgot that I'd drawn it that way. So I think you understand what the toroid is. You probably, if you've ever looked at any electronic circuits, you've probably seen some of this, especially like in radio circuits, like UHF radios or AM radios, that kind of thing. So anyways, we'll go with this. We have a hypothesis for our B. I'm going to go further and say that my DL is going to be R d theta hat. And now I'm going to say left-hand side, the closed integral of B dot DL is equal to the integral of B of R theta hat dotted with R d theta hat, which again, using the linearity of the dot product, I get B of R times d theta times theta hat dot theta hat, which I now make my drunken owl, and that's just one. See, it looks like a little owl to me. And the fact that it's evaluated on a constant radius r means all of this comes out in front, and I get B of r times the integral of d theta from theta equals 0 to 2 pi, which ultimately just gives me 2 pi r B of r. So again, we get a length multiplied by magnetic field magnitude for the left-hand side. Everybody follow that? Now the right-hand side is mu 0 I enclosed. Now, if you look at this, all of these enclosed currents are the ones on the inner ring. So they're the ones that are coming out of the page. And therefore, if I stick my thumb out of the page towards me, I see that my fingers curl in a counterclockwise way. So all of those currents are actually in a positive direction. And in fact, there are N of those currents. So I'm going to say the answer is mu 0 times capital N times I. So everybody see that that is the right-hand side? Anybody have any questions on that? So now I have 2 pi r b of r is equal to mu 0 n times I, which means that b is equal to mu 0 n times I over 2 pi r. Now remember, this r isn't the r that it was when we did a straight piece of wire. This is the radius of the big toroid. It's the big radius of the toroid, and it points in the theta hat direction inside and is approximately 0 outside. So
So when
that's,
we
go ahead.
sorry, when we measure the radius of the toroid, do we like, is it just like the to the inner diameter, the outer diameter, or like the center line?
If you actually did it, you try to measure it to the center line. And
Okay.
to be honest with you, the hypothesis is that the distance from the center line to the inside edge is a factor of 10 smaller than the r. And then the distance from the center line to the outside edge is a factor of 10 smaller than the r. So in some sense, numerically, it shouldn't make any difference whether you did to the inside edge or the outside edge.
Okay. So this wouldn't work then if you had like a toroid where like the coils were like wide, like
Yeah.
relative in comparison.
Yeah, if you had like a toroid that was proportioned like a bagel, this result would not hold up pretty well, would not hold up very well. Does that make sense? You see what I'm talking about with a bagel?
Yeah, would that still be something that you could work with this, or would
You
like you
can,
not be able to
in
do it?
that case, you'd punt by going to the law of Bios of art and opening up your computer and numerical recipes in C, or numerical recipes in Fortran, or numerical recipes in Pascal, or something like that, and then basically let it compute code wise. Or as an experimentalist, you just do an experiment and find out what the magnetic field is inside your bagel and go with it.
Okay, so in other words, that won't be on the.
Oh no, you're not going to have to do any stuff like that. Yep. So you've seen the 3 simplest scenarios that we're going to actually have with regards to this Ampere's law. Anybody have any questions about those? All right, let me show you an ugly one. Okay. So what I'm going to do is I am going to draw an oval. And then I'm going to draw another oval. And all these are supposed to be concentric. I don't know what this program's going to make it do, but they're supposed to all be concentric. And then I'm going to draw this as a straight line down, and this as a straight line down, and this is a straight line down. Oops. Yay. There I go again. So let's say, oops. I didn't like the way that line turned out, and I ain't got much time, but anyways. So this is a straight line down as well, like that. Okay. So that's really what we're looking at. And this goes on for infinity. So I should actually put for infinity, oops. And for infinity. And then I'm also going to draw down here. Hopefully this will work out right. That. And then that. And then I'm going to draw like this. And then hopefully this will allow me to do something like that. Okay, so it's a coaxial cable. Notice this is going to infinity this way. This is going to infinity as well. The middle one's going to infinity too. And in fact, what I'm going to do is, let's say the current I is going up that way. And in fact, a current I is going down this way. And assuming the currents are uniformly distributed over each cross section, what is B everywhere? Oops.
Do those eyes have the same value?
Yes, they have the same magnitude, but they're in opposite directions. And that's really what coaxial cable does to some extent. I'm going to also say that this radius is A, this radius is B, and this radius is C. And from that, you can see, okay, we're basically going to have a magnetic field inside it that's sort of counterclockwise as seen from above. So I would basically, if I drew my coordinate system, I'd orient my z-axis along the central axis in the central part of the coaxial cable, and my x and y would be my y would be on the page to the right, and my x would come out of the page. So that's the coordinate systems we're using. I want to calculate what this magnetic field is. So let's work on our solution. First off, my hypothesis is that B is equal to B of R times theta hat. So that's why I told you what coordinate system we're using and stuff like that. So what I'm going to do is I have to attack each of these little segments. So first off, I'm going to consider a Amperian loop that will be, an Amperian loop that's going to be smaller than A. In other words, its radius will be less than A. So first off, I'm going to say R, I'm going to say R is less than A. Left-hand side, closed integral B dot dl is just going to give me 2 pi R times B of R. And the right-hand side, this is the hard part, is going to be mu 0 I enclosed. Now, what we mean by uniformly distributed, we only got 2 minutes left. What we mean by uniformly distributed is that J is equal to a constant. And you might remember J from the drift velocity, but basically I is equal to the integral of J dot dA is what we're talking about. And it has units, for instance, to help you figure this out. It has units of amps per square meter. So being that it's uniformly distributed, we can say we can say J is equal to I over pi A squared for the inner one. R, it's equal to I over pi times C squared minus B squared for the outer one. Okay. So if I want to know what I enclosed is for a given radius R, which is that, then I enclosed is going to be gotten by, let me work it out down here. I'm going to say pi, I'm going to say I over pi A squared is equal to I enclosed over pi times R squared. So that gives you I enclosed is equal to pi r squared over pi a squared times I. So you can see that basically the pi's cancel out. And I'm going to now get mu 0 I times r over a quantity squared. Now you could also do it with that integral, but I would assume you don't want to do the integral. So it's easier this way. That being said, if I said the current density was proportional to R, or the current density was proportional to R squared, that's a way I could make this problem a little more complicated, and then you'd actually have to do the integral. Okay. So now that I have that, I can say left-hand side equals right-hand side. And from that, I'm going to get 2 pi r b of r is equal to mu 0 I r squared over a squared. So b is going to be equal to mu 0. Notice this r cancels out with one of those r's. So it's mu 0 I over 2 pi a squared times r in the theta hat direction for r less than a. Okay. Now, if we wish to do r is in between a and b, then I can do like this. And the next part says, by the way, it's now 6:40, so you guys are free to go. I'm going to finish this up. You can stick around if you have time. If you don't have time, you can just catch it on the video. The video will be posted probably in about an hour. So you can come back and check it then, but you're free to go if not. And I'm going to continue talking like you're here. So it's okay if y'all do split or not. Okay. Sorry for taking so long. But let's do the next part. The next part is going to be oops, got to take it off that. The next part is going to be done as A is less than R is less than B. So again, the left-hand side, I think you can tell immediately is going to be 2 pi R times B of R. And the right-hand side is really easy on this case because it's the entire current. And notice I didn't draw it here, but I should have. I'm integrating around this direction in all of these like this. And that's consistent with the I being in the positive direction. So the right-hand side here is just going to be mu 0 I enclosed, which is just, notice now that I've got the radius bigger than A, it's the whole current. So it's mu 0 I, and that happens to be in the positive direction. So I now get B is equal to mu 0 I over 2 pi R theta hat for R A less than R is less than B. But you can look at this and realize, hey, if I let R equal A in that first one we derived, then the A at the top is going to cancel out with the A squared in the bottom and just leave a single A in the bottom. So we can now say, oh, it's not just for R less than A, it's for R less than or equal to A. Okay. Now I'm going to do B is less than R is less than C. Okay. So I've got to draw another Amperian loop, but this time the Amperian loop has to have an R that's bigger than B, but smaller than C. Okay. Again, I'm integrating in this direction. So you see that the I in the middle is a positive, but the I on the outside is definitely a negative. That's the key thing to pick up on this. So when I go to do this, I have to do my right-hand side and my left-hand side again. The left-hand side, as you might suspect, is just going to be 2 pi R B of R. The right-hand side is a little more complicated. In fact, what I'm going to do is I'm going to say I over pi c squared minus b squared is equal to I enclosed over pi r squared. So you can figure out what that's going to be basically by saying the right-hand side, which is mu 0 I enclosed, is going to be mu 0. Notice the pi's are going to cancel out, and we're just going to get I times r squared over c squared minus b squared. So any questions on that? Now left-hand side equals right-hand side. Actually got quite a few of you left. Thanks for sticking around, guys. Sorry for running it so far over, but 2 pi r b of r is equal to mu 0 I r squared over c squared minus b squared. Notice all those units work out such that the r squareds cancel out with the units of the c squared to b squared. So everything is kosher that way. Also notice that this r cancels out with that r. And again, I get a linear type relationship so that we find b is equal to mu 0 I times r over 2 pi times c squared minus b squared. Any questions on that? Oops. One thing I forgot, that's the negative part. So hold on with that. Let me do it this way. So what I'm going to do is, since that's negative, I'm going to put a negative in front of it, but I also have a plain I like that. So that's where I screwed up. I completely forgot the other current. Let me go back and fix this accordingly. I was getting figures that I knew weren't working out right. And then I said, oh yeah, duh. So notice the I is downward, and that's a negative because the right-hand rule suggests an upward current would be consistent with the direction I'm integrating. So I had to have negative I r squared over c squared minus b squared, but then I have a plus I for the other part. So now when I set them equal to each other, I get 2 pi r b of r is equal to mu 0 I. And now what I'm going to do is I'm going to take 1, which is what I get from the positive one, and then I'm going to say minus r squared over c squared minus b squared, which I can also, let's actually change colors since I'm doing something kind of weird here. I'm going to simplify the right-hand side, but I don't want it to look like, you know, the right-hand side's equal to the middle part. So I'm just going to do it in a different color. This is going to be mu 0 I times c squared minus b squared, and then minus r squared over c squared minus b squared. In other words, I got a common denominator, and that's what happens. So I have c squared minus b squared minus r squared on the top, and I get c squared minus b squared on the bottom. So now I can finally say that b of r, I can say that b as a vector is in fact mu 0 I over 2 pi. Now, notice if I divide by r, actually, it's probably best to just leave the r in the bottom like this. So I'm going to say the r's down here, but then I also have a c squared minus b squared for the denominator. And then up here, I have a c squared minus b squared minus r squared. And all that's in the theta hat direction. So that's my magnetic field for B is less than R is less than C. But again, if you look back at the previous answer, you'll see that you can also write this as a less than or equal to, and you also see that you can do it this way as well. Now, finally, if you look at for R greater than C, I enclosed is I minus I, which equals 0. So B is equal to 0. And that's it. That is the entire problem solved. Like I said, if I wanted to make it a little more difficult for you guys, I would say instead of uniformly distributed, I'd say the current density J is some constant times R, or some constant times R squared, or some constant times R cubed, because all of those are easily integrable. And that's all you'd have to do. But that would require you to use that would require you to use this integral here. And of course, you have to choose something like 2 pi r dr for your differential area element and go that way. So does anybody have any questions on that? All right, we are done with Ampere's law. And you guys, of course, were already free to go. But if you have any questions, I'll wait around for the last one to leave. And thank you, everybody, for coming.
Thank you.
Thank you.
Have a great night.
You too. Thank you, Haley. All right, looks like that's it. Stop sharing. And let's say in. Thank you, Taylor, for letting me know toroid versus torus. Thank you. Why am I? Yeah, I was using TAURUS because I'm thinking of the constellation. I don't know what I'm thinking. Sorry about that, everybody.